Hi everybody, Mrs. Pesic here. Today we are looking at section 4.5, exponential and logarithmic equations. And our objective is to solve exponential and logarithmic equations and to solve problems involving exponential equations. Let's take a look at our first example. If we want to solve 2 raised to the 3x equals 2 raised to the x plus 1. This is an exponential equation because our unknown, our x, the variable, is in the exponent. Right? It's not in the base. So it's not like solving, x squared plus 3x equaling 7. That would not be an exponential equation because the x's are the bases, not the exponents. All right, but if we want to solve this exponential equation, what we're going to notice is that we have the same base on both sides. If we have the same base on both sides, it means that the exponents must be equal. So we can just say 3x must be equal to x plus 1. And then we solve this just like we would in Algebra 1. We get 2x equals 1 and divide by 2 and we get x equaling 1/2. All right, so that would be our solution for this first example. Let's take a look at the next example. We got solve 9 raised to the 8 minus x equals 27 raised to the x minus 3. Well, we cannot just say that 8 minus x equals x minus 3. We can't say that because our bases were not equal. But if there was a way to get those bases equal to each other, then we could solve this problem. So let's try and do that. If we're solving for x and we want to get the bases equal, notice that 9 could be written as 3 squared and 27 is the same as 3 cubed. So we really can write both of those with the same base. This would be 3 squared getting raised to the 8 minus x equaling 3 cubed raised to the x minus 3. Now we would need to distribute the 2, because we're multiplying. Remember, when you're raising a power to a power, you multiply the exponents. So this would be 3 to the 16 minus 2x equals, and again, we need to distribute over here, and we'd have 3 to the 3x minus 9. And now we have the same base on both sides, so that means that the exponents must be equal to each other. So now we can say 16 minus 2x equals 3x minus 9. And to solve this, we would add 2x to both sides, and we would get 16 equals 5x minus 9. Add 9 to both sides, and we're getting 25 equaling 5x. That was weird. 25 equaling 5x, and then dividing by 5, we would get x equaling 5 as our solution. All right. As a way of just checking this quickly, if we plug in 5, I would get 9 raised to the 8 minus 5. Is that equal to 27 to the 5 minus 3? Let's check that. That would be 9 cubed. Is that equal to 27 squared? Well, let's check it on our calculator. Is 9 cubed equal to 27 squared? I go to my calculator. On a calculator page, 9 raised to the 3rd is 729, and 27 squared is also 729. So it does work. All right, let's take a look at another example. This one says solve 4 raised to the x minus 1 equaling 5. Now here, these bases are not the same, so it's not going to be a simple task to try and get, the bases to be equal to each other. So what we're going to do for this problem is we are going to rewrite it in logarithmic form. Remember, this is an exponential equation, and it's in exponential form right now, so let's rewrite this equation in log form. That means we want log to the base what of what equals what. Just like we were doing on the video guided notes from section 4.3, notice the base is 4, so that goes right here. and the exponent is x minus 1, and logarithms are exponents, so that goes right here, and that leaves a spot for the 5 right here. So we have to solve log to the base 4 of 5 equaling x minus 1. And so if we want to solve this, we could figure out what is log to the base 4 of 5 on our calculator. We just go to the log button. This is not one that's going to come out to be a nice integer. We are going to go to the log button, log to the base 4 of 5. That's what we're trying to find. And when I do that, I get 1.16. I'll say 1.161 approximately. So I've got 1.161 equals x minus 1, and to finish this up, we would add 1 to both sides. So I would end up with 2.161 as my value for x. All right. So let's pop in a notes must do right here. For this notes must do, let's have you solve a problem that's similar to this one. Let's have you do 3 raised to the 2x equaling 5. Okay, so I would like you to solve this one, 3 raised to the 2x equals 5. And again, you're going to need to do that by rewriting in log form like we did in this previous example, and then using your calculator because it's not going to turn out to be something nice. All right, so that's your first notes must do. All right, let's take a look at the next example. Log to the base 6 of 2x minus 1 equals negative 1, and we're trying to solve for x. So now this is a logarithmic equation that we're trying to solve, and the technique for solving a logarithmic equation is to rewrite it in exponential form. So this is in log form. We are going to rewrite it in exponential form. All right, to do that, remember, this is our base. This is our logarithm, so that means that is the exponent, equals 2x minus 1. All right, and 6 to the negative 1 is 1/6. And so I get 1/6 equals 2x minus 1. And I can solve this nice little linear equation, add 1 to both sides. So I get 1 and 1/6 equaling 2x. And then I can multiply both sides by 1/2 to get my answer. And so when I do that, 1/2 times what would really be 1 and 1/6 is really 7/6. So I get 1/2 times 7/6. I'm getting 7/12 as my answer for this problem. All right, and let's try this one. In this example, we've got to solve this logarithmic equation, log to the base 4 of 100 minus log to the base 4 of x plus 1 is equal to 1. And notice we've got 2 logarithms that both have the same base, and there's a subtraction. That means that we can rewrite it as one logarithm to that same base. Are we going to subtract? Are we going to do 100 minus x plus 1 like this? No. From our properties of logarithms, we know that if there is subtraction, we are going to want to write it with division as one logarithm. So it's going to be log to the base 4 of 100 divided by x plus 1 equaling 1. All right, now how do we solve this? Now that we have it like this, again, this is in log form. Let's rewrite it in exponential form. All right, so to do that, we would take our base, which is 4, and raise it to our logarithm, which is our exponent, which is 1. I get 4 to the first equals 100 over x plus 1. So now I can solve this equation by just multiplying both sides by x plus 1. And I get 4x plus 4, if I distribute here, equaling the x plus 1's divide out, and I get this equaling 100, and I solve this the rest of the way. Subtract 4, I get 4x equals 96, and divide by 4, and x turns out to equal, I think that's 24. All right, so that is how to solve a logarithmic equation that might be really have two logs in it with a subtraction. Let's see. All right, let's solve this one. Log to the base 5 of x to the 4th is equal to 8. If we're solving this, we can rewrite, again, we have a logarithmic equation. The strategy is going to be to rewrite the log equation into an exponential equation. Okay, so we can do that. Just one thing first, before we do that though, we can rewrite, remember our properties of exponents, if we, properties of logarithms I should say, we can bring this exponent down and put it in the front. So we really can write this as 4 times log to the base 5 of x equals 8. That is equivalent, and that is still log form. But now it might be easier to solve for x. Let's clean this up a little bit first and divide both sides of this equation by 4. When we do that, the 4's divide out, and we're left with log to the base 5 of x equals 2. That's still in log form, but it's cleaned up now, looks a little bit nicer. And now we can rewrite it in exponential form by writing 5 as our base, raised to the logarithm, which is our exponent. Logarithms are exponents. So 5 to the 2nd equals x. So it turns out that x equals 25 as our solution. All right, and to check that, since we got 25, let's check that. Doing a little check here. Log to the base 5 of 25 raised to the 4th, is that really equal to 8? Well, again, from our properties, we can bring this down in front. So we're really saying 4 times log to the base 5 of 25 is equal to 8. At least we're wondering if that's true. Well, what is this? Log to the base 5 of 25. Remember, even without a calculator, you can do this one, because this is really saying 5 raised to what mystery power is going to give me 25? And the answer is 2. So log to the base 5 of 25 is really just equal to 2. And 2 times the 4 from right here is equal to 8. So it does work. We like 25 as our solution. Okay, let's do one more. This is actually for you to do. This is your notes must do number 2. I'm asking you to solve this equation. It's a logarithmic equation that you're solving. Log to the base 12 of x plus log to the base 12 of x plus 1 is equal to 1. And my suggestion for you on this problem is that you, just to get you jump started on this, that you rewrite, since we've got two logs with the same base, and we have an addition sign here, we can write it as log to the base 12 of x times x plus 1, right? We're multiplying this times this, all right? And then that has to equal 1. So that should get you started. That is in log form. So you're going to rewrite it in exponential form and then solve it like you know how to solve. All right. So that's it for this video, and we'll see you next time.